Hi guys, it's been a while. I haven't been up here. Mrs. Speckle is still teaching because I don't know any of this stuff because,
She's my
But
student.
I'm going to play the part of student. I changed into my calculus shirt, so everything's good.
Yeah,
And
I shed a
these
layer.
are our friends.
Brooke.
These are times when, you've got to stand 6 feet away from your real friends and just hang out with your virtual friends. So we're hanging out with Brooke and Colin today.
That's
All right,
right.
enjoy.
Okay, so let's see. I picked up Busani this morning at 8:30 a.m. on Friday, March 13th.
Also, cheers, Luke. Stay well.
Luca, there's some almonds. We have been here now 3 hours taping videos and uploading them to a YouTube channel. And she has eaten only almonds, and I have eaten
Nothing.
a burrito.
Oh, a burrito.
Oh, Brenna, Miss Butler brought me a burrito. And I had a tea. And she had told me to keep hydrating so that the virus doesn't get stuck in my throat. Right? Okay. Oh, and we visited Dr. Hill and showed him our socks because it's still Flamingo Friday. Okay, this is Brooke Taylor of the Taylor Polynomials. And this is the guy with the mad hairstyle, Colin McLaurin, who only got famous by taking Taylor's polynomial and plugging 0 into it. Shall we learn a little bit? Shall we learn a little bit? Okay. All right, so you might recognize this. I hope you do, my goodness, because we just learned this yesterday, even though I've taught 7 lessons since then. But yesterday, as in Thursday, March 12th, when you were in my classroom, we wrote this as a Taylor polynomial, and we expanded it, and we wrote all these really fun polynomials. And now the only difference is I have this big sigma in front, which makes it a series. So now instead of a Taylor polynomial, it's called a Taylor series at the center seat. Again, our thief friend, Colin McLaurin, with the mad hairstyle, C equals 0, is called a Maclaurin series. In my class, we assigned different people centers, and they got to name their own series. One person picked I. So anyway, you can have your own series if you're in Busani's class and you guys didn't do that. That was good times. I don't think I have any more to say on that. Okay, so you might also remember that we were using a Maclaurin polynomial recently to approximate sine of 0.1, and now we're approximating the sine of x, meaning that it's for all x. We're going to do this, write a series and determine the interval of convergence. So let's do this. This is basically we're going to put everything together that we've been doing this whole unit into one problem right now. And so I'm not sure how you did this, Busani, but when I did it, I had them do what we called calculus yoga, which is take a bunch of derivatives, and we were kind of driven by how many they said we should take. In this case, we don't have a number, so we're just going to stop at 5. But you guys can all look back at your notes, and you could also just generate these super fast. So I don't have much to say about this. But I do want to ask you, what's the center of this polynomial if it's a Maclaurin series? 0. Okay. So generate a whole bunch of derivatives, plug in the center, and you get a bunch of zeros. Okay? This is nothing new. All right? This is yoga. What we used to call a polynomial, we're now just going to call f of x, and we're going to write it out. And I'm going to skip a few things because I think you remember this. But the first term is 0, and then the next term is 1x, and the next term, the x squared term, is 0 again, and then the next term is negative x cubed over 3 factorial. If you don't remember this, look back at your notes from 9.7 in the next term. And so what we talked about, at least in my classes, was can we see a pattern, and can we write that pattern as a series? And we definitely could see a pattern, and we definitely did write a series. And the pattern was that this was alternating. What's another pattern that you see there, Busani?
It's an x to the n over n factorial sort of thing, except that we really want to do 2n plus 1 to get to the odds.
Oh, that's a good idea. And on the
over
bottom.
and 2n plus 1 factorial.
Okay. She's eating almonds, so I'm not going to ask her any more questions. She's very busy over there right now. So this is our approximation for the sine of x. And I guess I should say approximately equal to, because we probably should talk about that interval of convergence. Have we done this interval? Oh,
No.
yes, we have. I did this today, this morning at some point. Look back at your notes.
Oh, yeah.
Let me think. Remember, Busani was helping me with reducing,
The 2n plus 3 over.
yeah, reducing factorials. So from your old notes, and I want to say it was
From one of the
definitely
9-8 videos.
From old 9.8 videos, the interval of convergence is
Oh, real.
all reals. Yeah. So I don't think I mentioned, and I meant to, I told you I was going to do this, but when we had seen this series earlier, I meant to say, by the way, that's the sine of x. But I was just showing off because you wouldn't have understood what I was saying that for. But it is. This is the sine of x, and it is the sine of x because it works for all reals. And so it's super cool if you guys have nothing to do, right? You're sitting at home and you're bored, and maybe you have a little brother or a little sister who's sitting at home bored. Tell them to do this. This is super awesome. So you take your sine curve, graph it, and then start graphing. Just do this like incrementally because it's way cooler if you do it this way. Graph the first term of this, up here. Graph the first term, y equals x. Meh. That's pretty close, right? In like a little interval, it's pretty close. The second term, if you add the second term, it adds that like level of, like a whole new level. Let me do a different color. So the level of closeness increases, and by that I mean convergence, of course. And then when you add in your fifth term, it starts like it goes like this. Is that a fifth term? I don't know. I don't teach Algebra 2 Advanced, but my point is, every time that you add one more term to your approximation, it flips, and it moves out. So like it gets closer and closer, and just like adds curvature to the sine graph. I'm looking at myself with all these words all over my face.
There's no getting away from that.
I can't get away. Anyway, so the more terms that you add, the more sine it's going to look like. And if you have tons of time, go to like 900 terms. It'd be super fun. And you'll see it's spreading out. Because it's not just getting better in a little interval. It's getting better like outwardly. Isn't that cool?
Yeah, and what are you guys doing watching Love is Blind when you could be plugging in the 900th
Love
Taylor
is
polynomial
blind.
for sine x?
Yeah, love is blind. No. Okay. Is that all I wanted to say about that? I think so. Check my time for me, Busani, please.
You're good.
Okay. So let's talk about like.
Do one more.
Oh.
Whatever. Yeah.
Okay.
It was
Well,
7 minutes.
we're skipping that because we just wrote it like 2 times. Okay. So here's what I call smart girl versus dumb girl. So remember just on one slide ago, I had sine of x, and then I did the derivative, and I did the derivative, and I did the derivative, did the derivative, did the derivative. Plug in the center, plug in the center, plug in the center, plug in the center, blah, blah, blah. And then I wrote the polynomial. And that took a long time, and it was fun, and it was yoga, and I love it. But if you start doing what I call the dumb girl way, this is what a dumb girl's going to do because she doesn't have all the information that she needs. She's going to take sine of x squared. And by the way, the dumb girl is actually like really, really smart because the dumb girl knows the derivative of the sine of x squared. Do you know the derivative of the sine of x squared? Let's see if Busani is dumb.
Oh my god.
What's the derivative of the sine of x squared? Don't forget the chain
2x
rule.
cosine x squared!
2x cosine x squared. So remember, it's like this. Derivative of the outside, leave the inside. Derivative of the inside, chain rule. Raise your hand, everybody who wants to take the derivative of this. Raise your hand. Does that look like fun to take the derivative with the product rule and the chain rule? No, I don't think so either. This is a no thank you. And if you had to, you could do it. Of course you could do it if you had to, but I don't want to. I want to remember that rule that I taught sometime today that said that if you have a kx or an x to the n, remember I yelled n, you can plug that in to the function that you already have a series for. And we have a series for sine of x. We just generated it. The series for sine of x is negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So what do you think, Ms. Busani, the sine of x squared is going to be?
I think I'm going to replace x with x squared.
That's all? Is it that easy? Is it that easy?
God.
It is. The answer is yes. That's it. Like, that's it. That's what the smart girl is going to do. You are a smart girl.
Cool.
So this right here, oh no, undo. Quick, okay, highlighter. This thing right there, which goes with that thing right there, can be replaced by, and listen carefully to this, it can be replaced by kx, so like 2x or 5x or 10x, or it can be replaced by x to the n, where n is a constant. It can be x to the 1/2, x to the 5th, x to the 4th, x to the 2nd. What you cannot do is replace it with x minus 1 because the center changes. If the center changes, all of your derivative values are wrong because the way we came up with this was from using derivatives for our coefficients from the derivative of sine at 0, and the center was 0, and they were pretty, and they were 1s, and they were 0s, and it was cute, and it was a pattern. But if my center had been 2, all of my coefficients would be sine of 2, cosine of 2. It wouldn't be pretty. This would not be a series that would approximate that. So you can only do it for x to the n and kx. All right. Another way to do this, and then I have to stop because I'm going to run out of time here, is you can write the terms out, and the terms were like we've done before, but like this. I'll just try to jam those in there. And you can replace each one of those terms with x squared. So your first term will be not x, but x squared, and your second term will be not x cubed, but x squared cubed. And so you don't always have to do it in sigma notation. You can also do it by just replacing the kx or the x to the n in each term of the entire expanded series.
Wow.
And we're going to pause because that's super exciting. We need to start a new video.